Let's go ahead and look at ways to represent quantitative data. Once again, quantitative data is basically represented as a number. Now, the common ways to represent quantitative data is histograms and stem plots. They're very similar and related to each other. We also have time plots. There'll be other graphs of numerical summaries that we'll look at in the next chapter. Now, histograms, you might think look like bar graphs. Yes, however, with histograms, you have numbers going across your horizontal axes because you're dealing with quantitative data. When you're dealing with bar graphs, you have categories going across your horizontal axes. That's the main difference between them. Now, in this first bar here, it's representing all the states that have a percent of Hispanic population between 0 and up to 4.99. Once it gets to 5, it switches over into this next bar, and so this next bar represents all the states from 5 all the way up to 9.99. Now, looking here, you can see for the Hispanic population that there's one state way over here, significantly different. We would consider that to be an outlier, and in this case it happens to be New Mexico. Now, when you're making a histogram, there's no necessarily set way to make a histogram. Your bin size, meaning the width of your bars, is questionable of how many you want to use. You don't want too many bins or bars that have a height of 0 or 1. You don't want to have too few bars because you lose too much information. You don't want it so many bars that it's too detailed and doesn't give you enough summary information. For the most part, you're going to want the number of bars to be between 5 and 10 bars or bins. There is no perfect way to do this. So you look at your data, you see, okay, if it goes from 5 all the way up to 50, and then say, okay, if I wanted 5 bars or 8 bars or 10 bars, somewhere in there, divide it and it'll tell you how wide each bar has to be. Then you count up how many pieces of data fit for each bar. And then you want to draw your histogram and make sure you include your labels on your histogram. Now here's an example, 5 examples of histograms all dealing with the same information. It's all the same data. Now these first two here, we're not going to be real crazy about because there's too many bars, it's way too detailed. When we get farther down here, this last one still contains the same information we had up here in the top, but we don't like this last one because it's way too summarized. It only has 3 bars. Everything's kind of summarized too much. Now, here's 2 examples that are acceptable. They do look a little bit different, but there are some similarities. This one here has wider bars, but they both have 5 to 10 bars apiece. Both of these would be acceptable histograms. Now, when you're looking at a histogram, you want to look at the overall shape, how far the histogram goes from left to right, meaning the spread, and you want to look at where the center is, meaning where's the middle of your histogram, where's the middle part of your data. And then you want to look at the overall shape. When we're talking about the overall shape, we're talking about not the detail connecting the heights of the bars, but what's the overall general pattern of all of our data. And in this case here, it's kind of a smooth curve going like this. You might say, well, it cuts this one off, goes above this one. Yes, but we're looking at the overall general pattern. We're not looking at the detailed height of each bar. You also want to go ahead and look at any outliers, any pieces of data that are significantly farther to the right or farther to the left compared to all the other data. We also want to look at giving our histograms shapes names if it fits into one of those categories. Now, looking at the one here on the right, we would say this is a symmetrical piece of data or a symmetrical distribution. For the most part, you could draw a vertical line right here in the middle, fold the right half over that vertical line, and it would be on the left half. Is it going to match perfectly? No, but for the most part we would say it's symmetrical with the same on each side of the middle. We also have, in this situation, a skewed to the right data. When your data has a tail that's going off to the right, and a tail I meaning where it goes down and there's only a few pieces of data going off here to the right, we would say it's skewed to the right. Now, if I go ahead and flip this, we would now say it's skewed to the left because your tail's going off to the left. So when we're talking about skewed, you're going and you're referring to it being skewed in the direction of the tail. This one over here, we're going to say does not necessarily fit symmetrical or skewed. We would say this one kind of has three peaks, so we would say it's either a complex or multimodal. Modal referring to the peaks, multi meaning more than one. But we're not going to get into this a whole lot. Typically with our data, we're going to be talking about symmetrical, and we're going to be talking about skewed. Now, outliers are observations that are significantly different than all the other pieces of data. So as we look here, in this case, we're looking at states with residents over the age of 65. We really have two outliers. We have Alaska. Alaska's not necessarily a high retirement location. And then we have Florida, which is where a lot of people like to go and retire. So we have two outliers in this piece of data. We also have stem plots. Stem plots are related to our histograms, and we'll see that shortly. But for the most part, we have our stem plot over here. We have our stems here on the left, and we have our leaves here on the right. Each number here on the right represents one piece of data. So if we're referring to this 9, since that 9's in the 40 row, we would say this piece of data represented by the 9 is a 49. This one right here is a 2. Since that's in the 20s row, we would say this piece of data, this 2 right here, is representing 22. So the number on the left is your stem, which in this case is our tens digit. The number on the right is our ones digit, representing each piece of data. So now if you look down here at our original piece of data down here, here's all of our data. So here you can see your 70 here at the very end. Your 0 tells you the ones digit, and you're in the 70s row. So this is a 70. Here's some data dealing with weights. Now, on the last problem, we only had one number over here. Well, depending upon your data, you may need to have two numbers over here. And so a 192, your 2 is going to be the leaf, because each leaf has to be represented by one number. So you're going to have a 19 to the left of the bar. So looking at all this data here, all the way through all the pieces, you would go from 10 all the way down to 26. And you have a key here. For each stem plot, you should have a key that lets you know how to read your data. So if you had a 20 with a 3 on the right, that would mean 203 pounds. Once again, our stems are tens. And so if we have our 15 with a 2 after it, that's our piece of data of 152. Or our 13 with a 5 after it is our piece of data of 135. So if we go ahead and do that for all of our data, we would get something like this here. Now, stem and leaf plots can actually be extended, and they can be extended by going ahead and breaking your stems into pieces. Sometimes you're going to have a lot of data that fits in a small area here. So with that, you can go ahead and break your 150s into two smaller categories, where the first 15 is representing 150 through 154. The second 15 is representing 155 through 159. And so Anything from 150 to 154, you'd put the numbers to the right over here. Here, anything that's in 155 to 159, you would put the numbers here to the right. This is going ahead and splitting your stems. Now, histograms and stem plots. Here's a stem plot. Basically, a stem plot and a histogram are representing the same information. All we have to do is go ahead and rotate our stem plot, and we end up having a histogram. But they're still representing the same information. So, let's go ahead and answer these questions. And in this case, our 28 is showing up with 3 different 8s in the 20 column. 1, 2, 3. Oh, sorry, don't get that 9 in there. Since our 8 showing up 3 times in the 20 column, we have 28 showing up 3 times. Once again, pause the video and answer these questions. Here we're looking at the $1,441,000. That would be from here to the left. So we're looking at the heights of the first 2 bars. So we're going to add the heights of the first 2 bars together. So you take this height, go over here, tells you how high it is. This one here tells you how high it is. Add those 2 together and you get 100 or 220. Now, sometimes your histograms don't necessarily fit a particular shape. Well, that's okay. Don't be thinking that all your histograms have to fit a certain shape, or if you have a large enough data set that it's going to fit a certain shape. These 2 histograms don't really have any shape that we would necessarily call them or categorize them as. Let's take a look at time plots. Time is going to always be on the horizontal, and then what you're measuring goes on the vertical. And so in this case here, you're measuring the price of oranges, and so you can see where it goes up and down, and you have seasonal variation that occurs throughout the years. But overall, the overall pattern is upward. And so you want to look for variations. You want to look for either an upward trend or a downward trend, or if it's not changing at all. So time plots are useful for those things. Here's an example where we have tuition of public and private schools, and you once again have time on the horizontal, and you can see where in each case you have an upward trend. Notice the private has a higher upward trend than the public. Time plots often show cycles, seasonal patterns, or repeated patterns, either a trend upward or a trend downward. Histograms and time plots give totally different information. So here we have several time plots that are all representing the same information. However, the scales are different. You don't want too much empty space. So here we have a lot of empty space on the bottom. We don't like that. We don't really want it to be too compressed. Now, typically you want your time plot to cover the majority of your graph. So in this case, we changed our scale so that we started at a height of 120. But keep in mind, when you're looking at any graph, you want to look at your scale, because some people will try to give you a misleading graph to get a certain point across. So be aware of your scale. Scale matters.